Now for the blue team perspective of how we can detect the activity we've undertaken in the previous part of this video. What we're going to cover is from the Elastic perspective. So I would like to introduce that to you today. And of course, you'd need the blue team part of this lab set up. So if you only focused on the hacking side, then perhaps the rest of this video isn't for you. But if you are interested in how a defender or a blue teamer may see the activity that you've undertaken, this part of the video is definitely for you. What is the Elastic stack? Previously, it was called the ELK stack. Now, however, it's just referred to as Elastic. It is a suite of open source products designed for a logging use case. So, generalizing, it is a data construct based on Apache Lucene that then gets packaged as Elasticsearch by Elastic, that has other components that are important for us today, which are Kibana, which provides the GUI, Logstash, which we aren't using in the Tartarus lab, that provides a data pipeline connector, Beats, which we aren't directly using in the Tartarus lab. However, the components of Beats are already integrated into something called the Elastic Agent, which gets installed onto an endpoint such that you can do some EDR, endpoint detection and response capabilities, and like a traditional logging agent, you can get logs from that remote system to your centralized SIEM, the Security Incidents and Information Management System. How I've configured it is very much a SIEM use case. You can also configure Elastic to do just about any sort of storage construct imaginable. There's more advanced machine learning applications for it as well, where it can do semantic search and that sort of stuff. We're not going to worry about that today. We're merely using it as a bucket to pour all of the logs that we've created from OpenSense and the Apache instance into, so that we can search through it in a structured manner and then create alerting logic off the back of that. You can also connect it up to any host of webhooks, and then you can get notifications via Slack or notifications via Teams or notifications any which way you'd like to get them based on these alerts. However, in the free version, there are some limitations. We won't be able to do that in this guide. Like it says here, it has some EDR, endpoint detection and response capabilities. I am turning that off in the deployment scripts. So we're going from the malware mode, which would normally be protect, to just detect. This then allows us to do all of this activity and not have the agent just zap us, because we wouldn't want that, because this is to demonstrate if a threat actor was able to bypass those preventions, you're going to want to detect it. Then all of those different components, so the Elasticsearch instance where data is stored, Kibana where we visualize that data, the Elastic Agent or Beats, how we ship that data from endpoints to the Elasticsearch instance. That is a general overview of what comprises Elastic and how the specific use case we're using it for today. You could use something like Waza or something like Security Onion. I've decided against that because we just go to the source. It'd be with Security Onion, it'll be open search, because Elasticsearch kind of went to a bit more of a proprietary license, but they're open source properly again now due to some kerfuffle with AWS and how they were interpreting licensing and then offering services. We don't need to get into the weeds, but why go through a middleman when you can just go directly to the source and use Elastic itself? What you're going to want to do is to add the domain name to your local resolver. You can either do that through a administrator PowerShell window if you're on Windows, or through Linux. You can do a sudo bash c, and then essentially this is just going to append what we did previously manually to your etc hosts file. If you've noted down the password from the previous step when we deployed the SIEM, that's when you'll use it now. So I've already done this, meaning I don't need to now. However, it does resolve correctly to the local IP address and domain name, and I've already logged in, so no need to worry about that. If you wanted to check on whether or not you can access these things, there are some commands you can use here, but we're not going to worry about that at the moment. Definitely, again, make sure the time zones are correct, because if they aren't, then you're not actually going to see the logs when you should be seeing them. So if you aren't seeing logs that you should be, or that you suspect you should be seeing, increase the time look ahead into like the next 12 hours and then the previous 12 hours. And then that should give you a really good idea of, oh yes, we're putting logs into a bucket that we're not actually looking at the moment. Because what Elastic, or what Kibana is doing, is it is interpreting which time zone your host is in, looking at the logs to what would be normally the UTC logs that Elastic uses in the backend. So that's just a little bit of an aside. Now, how do we configure these things? Like I demonstrated in the Blue Team prerequisites post, it happens in the ES Bootstrap and the firewall.php. So firewall.php, for example, these are all the firewall rules that get set. And then at the bottom, we supplied with a syslog destination, being our 192.168.56.10 IP address, which is the one Elastic uses. Some basic settings as to which port we're going to be sending it to. So we don't send it to the default 514. We're actually sending it to 5514, which is set up from the Elastic Fleet agent to listen on that specific port for any incoming syslogs messages. Yeah, in the ES Bootstrap. So it's a specific policy that gets applied so that it can listen for that syslog, those syslog messages. So we're primarily today focused on the firewall. If you don't have a firewall, there would probably be, if you're in the cloud or anything like that, there'd be AWS CloudTrail or some other solution that you'd be able to extract these logs from. I'm primarily focused on a firewall perspective today because that's something that we have already in the Tartarus lab that we can then use to generate another logging source. This is something that, of course, in enterprise you'd have a Juniper SRX, you'd have a Cisco, you'd have any abundant host of firewalls to manage your infrastructure within a DMZ. So you'd, for instance, you want to host a new website and you don't want to go to the cloud because you've been to the cloud, you come back again, blah, blah, blah. You can host it on premise, but you do that through something like a DMZ where you could say, okay, the internet is allowed access to this machine, but this machine has very, very limited access to any internal resources. So that if that machine did ever get compromised, it's not going to be able to be used as a pivot into your network, but you could still be able to manage it from within the internal enterprise network. What we're going to want to do is run an mmap scan. So like we did in the previous example, this is just a bare bones. We can clear that. Just a bare bones scan. Sudo nmap, and then A for doing all the tests, and then actually I'm going to specify here, so to be the SYN scan, and then any port, all 65,000, and make it very verbose, and then your target. So as that scan is compiling, we can now go into where we need to be in Kibana to be able to view these logs live, because we don't have any alerting logic for this type of activity, let's say hypothetically at the moment. So we need to look at the specific log sources. The first thing you're going to want to do is to make sure everything in Fleet is green. So we have Tartarus, not that we're specifically interacting with it. We are interacting with it, but we're interacting it via the firewall. What you actually want to look at is the Fleet, so the Fleet policy. This one's reporting all green, and then this is the specific integration that's getting the syslog messages, and it's healthy. So it's all good. So it's healthy, it's all good. So now we can look under, if you look in the burger tab, under discover, you will see it'll default to metrics. We don't want metrics, we want logs. So if you select the logs tab, then we can log in again and view it. Thank you very much. In the logs tab, you should see, oh wow, 10,000 logs in those buckets over this period of time. That is pretty loud compared to our baseline of 125, 79 logs per bucket. Now we have 8,000. It's over 9,000. That's that type of thing. You can see there, okay, 12,000 records for that specific bucket. Most organizations wouldn't be logging to this extent on publicly accessible infrastructure. Ideally, they should be, but there are instances where this level of logging may just be too verbose. So there are ways and means around this. However, in an ideal world, there will be this level of logging for the publicly accessible infrastructure, so that you'll be able to see, oh, okay, now this is a drop in the ocean compared to how much logs a normal web server would actually be getting. However, it does illustrate that, okay, we can see an increase or a delta between what is baseline and what is happening underneath an aggressive SIEM scan via Nmap. So you can see, okay, the scan looks like it's completed. What are we totaling for the amount of logs? 45,000 logs for that period of time. It's quite a lot. So let's confirm that the scan has indeed completed. All of those logs just to say there are 2 ports open. I mean, it's quite interesting. Now, done the scans, explaining sort of some of the areas and sectors within the screen. So you have here the available fields, the available ECA, the Elastic Common Schema fields. Then you'd have the viewer here. It does some sampling where you're only actually getting like the top 500 records in terms of like these sort of statistics, something like that. They're calculated from X number of sampled records. We don't need to worry about that at the moment, but this gives us a breakdown of each of the logs. So you can see here, if you click that, it'll give you exactly what that log is for, all of the details for that log. So let's say I'm not interested in any of the other logs. I just care about the event.data set that is pfSense. Wait, that is pfSense. It's called pfSense log because OpenSense is a fork of pfSense. So some of the stuff on ground level is still very similar. So there isn't a specific OpenSense log because they both fulfill the same role because it's a fork. We want to see, okay, that's sort of trimmed down. And now this is only the pfSense logs from the firewall. So when we click here, we can see, okay, the specific agent name, the specific data set, data stream is pfSense log. And then we've got some grok failures. So I'm actually going to do that. We don't need to worry about these grok failures at the moment. Grok it's not the AI, blah, blah, blah. It's a wrapper around regex so that you can declare things via keywords as opposed to the specific regex notation. That is how the logs get passed when they are ingested into Elasticsearch. So don't worry, it's not the actual AI, AGI, blah, blah, blah. We can see here for the specific log that the grok does pass. You can say, okay, the agent type is a file beat. So that gives us an indication to how these logs are perhaps being read and transported. Then it gives us some more metadata that we're not, don't need to worry about at the moment. Then it's going to give us this destination IP address. So our web server is 56.71. It's going to give us what category, so network. Now this should be, what is the destination? So you can search in here, dot port. So destination port 22, this should be allowed. So if we look at action, the event.action is pass. So we can see, okay, for port 22, it is allowing access. But then for other ports, okay, there's no port 22. Is there any that's not 22? There you go. Okay, 9200, also pass. Destination port 80, pass because it's the web server, so that's allowed. If we can find one that's not, okay, wait. So we'll just do a filter. So, and not destination dot port equals 80 or 22. Sweet. So now this should give us a breakdown of, okay, block, what port number, transport ICMP. So this is probably a ping. So it's attempted to ping, because ping doesn't operate on ports. It's a separate protocol. So we can see Nmap has attempted to ping the target and it's now been blocked. So you can see here, okay. So it looks like we're only allowing port 80 or 22. We can test that hypothesis if we do a psense log and event.action pass. Okay, now we can do a breakdown of the field. If we want to look at destination port, we can see here, okay, port 443 is allowed, 80, 22, 9200, 123, and so 123 is NTP, and then 53 would be DNS. So those are the only ports that are being allowed access from our hacker zone to our target zone. So that's not necessarily 100% correct, because you'd have to say here and destination address is my 192.168.56.71, and now this will give us confirmation. Okay, so it's only 443, 80, and 22. So it's more like web traffic and then SSH. This being a web server, that does make sense. So here's just breaking down exactly how and why each thing has to be set. We can put this into a visualization. We're not going to do that at the moment. You can follow the guide to be able to do that, but we don't need to do that at the moment. Where's my logged out? We'll be back. We're not going to worry about creating the visualization in this guide. Instead, you can follow the blog post and then be able to create the visualization. No stress. It has its uses. It's very useful in specific circumstances. However, we're not going to worry about it. Instead, we're going to skip straight to writing the rules and using the new ES pipe QL or ESQL to be able to identify this activity, as it is a much better, in my opinion, search construct than what they provided previously. So we're going to copy this search. So it's essentially from logs, where very similar to SQL with some key differences. It's not 100% compatible with SQL and SQL-like languages, but it does provide a great foundation for these searches and to do some correlation rule stuff later that I will demonstrate. How you interact with it, at least as of the version of Elastic within Tartarus at the moment, is a try ESQL button over here. It may change. There may be somewhere else. We're not going to worry about that. Here it's going to say the default search is from logs. Any of the log indexes is what we refer to. In more traditional database constructs, it may be referred to as a table, but because this is a reverse index search, it is referred to as an index, much like something like Splunk or the other SIEMs. We're going to then paste that in here, and then this is the search that we are going to run from logs where event dataset pfSense like we did previously. The event provider is the filter log, so we don't care about anything else happening on the pfSense firewall. We only care about the network activity that has been logged by the filter log. Then we can say a CIDR match. This is dropped in the rule because it's not really necessary, but you can say a CIDR match where destination IP address is any of the, this is not any of them, there are others, we're not going to get into that, but the predominant internal private IP addresses reserved under RFC 1918. The event action would be block, as opposed to the other event action that we looked at previously being pass. Where timestamp is less than, is 5 minutes, like from 5 minutes ago to now, then we're going to do a count distinct on the destination port by the source IP address. So this is one of the filtering things. You could do just a general count, but then that'll give you the total. We don't care if it's hitting the same port over and over again. We care about a count distinct. Then here I'm going to set the time frame to be, let's say, in the last hour, and then now minus 60 minutes. 60, almost 60. There we go. And there you can see all of the records that were recorded. 47,774 events that we can identify with that search alone. There are other ways to visualize it. It could be a pie chart, it could be broken down, etc., etc. And then finally, we're saying where the attempt count is over 1,000. We don't care about if you're trying one port every 4 hours. If that's your risk profile, these aren't the searches for you. These are not the droids you're looking for. Now we can do the fuzz foster ufool scan, or not scan, but reconnaissance. I'll couch this by saying these logs are not from the firewall. They can be from the firewall for the specific SYN requests, as we looked at in the red team post. So if it is a TCP packet with the SYN header flag set, you can look at it that way, or you could look at it from the specific website and what the Apache access logs would be seeing. There's a little bit of a side channel in terms of how you get being one of the methods to request a web page. So how you get web pages. This is primarily to illustrate you have to in detail understand the logging source, and also to attack things successfully you also have to understand how they have been implemented and what protocols they will follow. Just demonstrating with a basic browser to the damn vulnerable web app. So we can demo that. We'll do it live. It does this. I don't know why it does this. It logs you out. Yeah, it's one of those things. We're not going to worry about that. So here, if we do a little inspect element, we can see in the network tab, it's slightly different in a Chromium-based browser, but the principles remain the same. You can see that we've done a GET request for security.php, but the servers responded with a wait, a 302. So we need to be redirected to the login page. Then it goes, okay, get login.php, and then it responds with a 200. Now, as we watch, it's going to do a post request to do the login. So you can see there, post to login.php with the specific headers and the specific content being under the request, admin, password, login, and then user token. There's some fun stuff we can do with the user tokens or not do with them later on. We're not going to worry about that at the moment. But you can see here, these were the fields that we filled in that form to then be submitted. There's some other stuff that we're not going to worry about too much now, but that's essentially where you get, post, head, and trace are put, delete are some of the keywords in regards to HTTP methods. When you're interacting with an API, like in the Tartarus configuration script, which I'll show here, it does a lot of this stuff. I've had to write a lot of this stuff, how it interacts. So there is some post. So we're telling curl to post. I'm being explicit here with curl to say post, but if it has data, it assumes it's a post. But then I believe there's also a put request. So then that updates a record, traditionally as understood by APIs that are implemented. Post would create it, put, you can then update it as you go along. And then I believe there's also some explicit, is there some explicit get? Yeah, here I'm saying explicitly telling curl to use the get method. These are some of the ways that you'd interact with an API via the specific HTTP methods. If we wanted to look at what methods are available, when we ran the nmap scan in the output, as opposed, I mean, I was being a bit facetious last time when I said, oh, it's just 2 ports. It does also give us some other information in regards to what methods are allowed to interact with the web server. Supported methods: post, options, head, and get. So that gives us post to be able to log in. Options returns a list of available methods. Head should act exactly like get. However, no content should be returned in the message body. We can keep that in mind for this is what we call in the business foreshadowing. So a brief overview of the different HTTP methods. You can also view these things if you use curl in the verbose. So here curl v and then L to follow some links in the verbose mode. We don't need to worry about that. You'd also get the HTTP request responses from the server. So whether it's in the 500 range, whether it's in the 200 range, or whether it's the most common 404 not found, that would also give us information to be able to unpack from the server, because that all has to happen server side. Again, forensically, we're interacting with the server when we make these requests. We can't magically, it's not like an mnap zombie scan where we can ask another, by the sequence counts on a remote server, we can ask that server to then scan another server. It's not like we're directly interacting with the server here. So just keep that in mind as well. Obviously, VPNs, Tor, all of that stuff would come into play. You're not going to be scanning a target with your actual IP address. Let me just say. We can then, moving on, using fuzz foster ufull, so it acts, we can look at we've looked at the OpenSense logs, so the firewall logs. Now we're going to be looking at the web logs from the Apache web server. So I believe everything should be installed that I can just run this command. And clear the screen and then Control-Shift-V and then run the command. It's going to then do a more targeted fuzzing attempt. Previously, we fuzzed for the what subdirectory the damn vulnerable web app is going to be served at. Now we're fuzzing for any directories that are being served under that. You can see here git config, git ignore, all of these stuff that would indicate that this is from a Git repository. Then we have database, docs, and some other stuff. Security.txt, robots.txt. Very interesting. .git, very interesting. The reason we know that these things are there is that the server is responding to the GET request with a response code of 200. So we can then go, okay, let us have a look at the gitignore file, for instance. There we go. So all of these files are to be excluded from the source control. You say, okay, wow, hackable uploads. That's potentially interesting. And then you can slowly pull on the thread of what is available. This is demonstrated more succinctly in the upcoming brute force, because some of the information we need is actually within that directory. But just to give you a flavor of how we would use a reconnaissance scan, and then to look, okay, what has Elastic picked up of this scan? So we again go back to the Discover tab and then look in the last maybe 15 minutes under, again, logs, a small uptick, or a rather large uptick of 5,000 records. We can then right click and then we could say, okay, but here I'm just going to click on it, and then that will zoom in on that block. Then again, you could just hold and click, and then you could say, okay, give me that specific slice of time. Now we can look and say, what is this? What is this file? Beat, Elastic. Okay, we don't care about any of these record types. So that can go. Then network socket created. Do we care about syscall? I don't think we do. That can go. What are we left with? Some process events? No. So event data set is Apache access. Give me the access logs. Thank you. Now we want to look at the target URLs. We can then add this to the display here and see, okay, the fuzzfasterUFull attempted to enumerate all of these different directories. So we can see all of the different directories it has now attempted to enumerate. We can then look at, say, okay, this X login, I want to see what the source IP address for that specific request was. In here we could say source, and you say, okay, the 192.168.56.200, so that's the Kali instance, has attempted to access this specific directory. Very interesting. So you can see here, that's briefly what we've covered. And then you can also pin things to the viewer so that you could pin the request method, the response code, the source IP address, and whatever else you want. Now we can say, okay, well, in these requests, we can look at something that should be common to all of them, would be their user agent. So you can see here, the fuzzfasterUFull user agent. We'll just search for that then. That's not entirely the best idea, because a user agent is something in the attacker's control. They can change that to whatever they want. Later on in this series, we will look at changing that to something really malicious. We're not going to be focusing on that at the moment. What we're going to do now is just look at changing the user agent to something that's not easily identifiable, because this could be changed into anything. It could even be removed entirely. I mean, if you want to do that, I don't know why you want to do that, but you can do that. I'd personally, I just want to blend it, really. But you can also then look for the Nmap user agent as well. So to demonstrate that, you can run that for the last, because the time we're looking at a tiny little time window, we're going to say the last 1 hour. Cool. Nmap has tried to enumerate these directories. Interesting. Very interesting. So you can see here the details around that, and then I'll remove this filter and you can see all of the details for that log. We're not going to worry ourselves too much. However, here, this is another way we could have run the fuzzfasterUFull scan. We're telling it to use a specific user agent. We're saying, hey, this header field, because that's all the user agent really is a header field. Instead of using your normal one, why don't you use this one? So that we could blend in with the rest of the surrounding traffic. In theory. We're going to then also run the scan. The word list, let's say common, it's a great word list, but actually today I'm feeling pretty big.txt. Just do it. I mean, how long is it going to take? How long could it take? I mean, it's not like it's already done. I mean, so now that would be how many requests? 20,500 requests that we've just made to the target server. We've hidden our user agent, yes, but what does that look like? What are the actual consequences of doing that? Well, let us remove this filter, clean that up, the last 15 minutes as our time frame. So what an adversary would probably do is something like T for the thread count, let's say a T4, for instance. Is it not T? Is it, what is it in? Wait. Is it lowercase t? It's lowercase t, of course. Because it'll default to 40 concurrent threads. We're going to lowercase t, 4 threads. So now you can see the requests are happening a little slower. It's a little more manageable, which should have happened. Yeah, 4 threads. It's still pretty quick. In reality, an adversary would probably run 1 or 2 requests per second. So that's 86,400. If it's 1 every second, it's 86,400 requests every day, all day. They wouldn't, of course, be running that request from the same IP address. If they've got a botnet, they'd be running it from multiple different hosts. If that is your threat profile, again, these aren't the videos for you, but that's what an adversary would do if they were sophisticated. So now we can look at, we've had a look, again, here's just demonstrating, if you looked for the FuzzFaster full user agent for that specific time window, you're gonna come up empty because it's not using that user agent. We can then take a step back and go, well, what is the actual activity that's happening on the server? What are we generating on the server? And that is a signal that we can then use to be able to identify this type of activity. So we're going to say, we're not serving every single item in the adversary's word list. We're probably not even serving 0.1% of it. So instead we could say, any responses with a 404, that's what we'll use. So here we could say, in the last 5 minutes, give me all 404 responses and then sort them by the user agent and the source IP. Moving back again to the ESQL, we can then run that search. Say, very interesting, very interesting. We can see that this specific source IP address with this user agent has ran 40,000 requests. Very interesting. Similarly, why not just run another request with the normal FuzzFaster full, just to demonstrate, just to show that yes, this does in fact work. So we're going to remove the user agent part of this and then rerun the scan. This is the one with the capital T, isn't it? There we go. And then blistering breakneck speed. Again, to a normal target, this would probably look like a potential DDoS. So just bear that in mind. You don't really want to run this as aggressively as I'm running within the local lab. Now let us have a look at what this looks like now. Oh, there we go. There we go. So now we can see the two user agents from the same source IP address. Something's a bit suspicious, shall we say. You can modify it even more. Foreshadowing. You can modify it even more to make it look like something like this, where you can say from any of the logs, we want to look at the request method being get and then the response being 404. Then attempt count via the URL path by the specific source IP. We're going to sort that, and then where the attempt count is over 1,000. So we're going to run this search now. And you see here, okay, this specific source IP address has run a lot of searches. We can then increase this time to be the last 40 minutes. You can see, okay, that's the total number of requests that are being logged by the server from that specific source IP address. So now it's a bit more rule ready. So we can go through and create the rules manually within Elastic. So I'll demonstrate that now quickly. So we'll take this as our example. We will hit the burger menu and then go down to security, rules. Then we were presented with how we want to create the rule. We would like to make a detection rule for the SIEM. If you wanted to make another type of rule for something like a server that's CPU usage is too high or whatever, you can do that in the observability submenus. You can do an alert here within observability. So it's a bit of a different kind of alert, and it's beyond the scope of this video, but just note that you can do alerts in quite a few different parts of Elastic. So we're going to create a new rule. We're going to define it as a ESQL rule type. We're then going to do the ESQL query. We can then do a rule preview, so we can see how many rules this would hit, which is 3 over the last hour. Then there's a lot of metadata that we can fill out. So we're going to continue. We're going to give it a name. Let's call it name, a description, SDF, because we don't need to worry about this too much. This is just to give you an example of what you can do if you wanted to create your own rules manually. There is all of that capability within Elastic. The risk score, it could be 9, it could be 100. This could be like the most critical thing that's ever happened in the organization, or it could just be a Tuesday. Today's going to be a Tuesday. Tags, all that stuff, you can do that. Continue. The rule schedule, this is very important. So this is how often the search will run to be able to generate alerts from that rule. So if you set this to every 10 hours, then it'll do the search every 10 hours. Looking back at the time scale that you've indicated either within the rule context or some other metric. But here, we're just going to keep with the default every 5 minutes and then an additional look back of 1 minute. Then here is how you can integrate that. If there is an alert, you could put it in Jira, you could put it in Slack, you could put it in the Hive, you can do all sorts of stuff with it. At the moment, we're not going to do anything with it. So we're just going to create and enable the rule. This is the rule page for what we've just created. We can then look under the alert tab for any rules that would get run. There's a whole lot of other stuff going on. Don't worry about it. But we can see here a rule with the name that has been created. So that's how we can then manually test these rules by invoking that same action, or through the Omega CLI, you can automatically, through a combination of templating, run the malicious activity and then be able to get the alerts back from the SIEM. So this is the search that we've just done. You can also do like MITRE ATT&CK, the adversaries, tactics, techniques, and common knowledge stuff. The trademark. We don't need to worry about that at the moment. Instead, we're going to go to the Sigma rules. This isn't going to be a vast treatise on Sigma. I mean, this video is already over almost an hour long, so it's not going to be a vast treatise on Sigma at the moment. There will be one. Watch the space. I have already imported a lot of these Sigma rules for you. So I've written them. They're in the Tartarus lab. They then get, at the moment, manually converted to a format that Elastic accepts. And then in the deployment pipeline, those rules then get ingested into the SIEM. We can confirm that by going to rules, detection rules, SIEM. We're not going to be creating rules. We're going to be instead searching for rules. We're going to search for Sigma, and then this will give us a list of all of the Sigma rules currently integrated in the SIEM. Activity, we have the pfSense correlation rule, which we can have a look at. We're not going to worry about the threat hunt stuff at the moment because it's not necessary. We are going to look at the only imported the threat hunt. Odd. There should be two rules for this, a threat hunt and a normal rule. For some reason it's not importing the normal rule. Okay, that's something I'll work out offline. But here you can see this is the rule, correlation rule to detect the blocked network events from a single source to a single destination via a single observer on over 200 unique ports. That's why it's disabled, is 200 unique ports could happen all day, every day. So we're not really for a whole day. If you wanted to do some threat hunting though, you'd want a rule like this. If you don't want to do some threat hunting, this is not the rule for you. Then there is another rule, the detect hack user agent. This is a rule based on the creator of Sigma, Florian Roth. He has the hack tool user agent rule. I've made some modifications to it, so it can be a correlation rule for the activity that we were doing. We don't want 47,000 alerts. Instead, we just want one alert for that time bucketed so that someone can investigate it. Then there is the directory enumeration rule. This looks for, like we did previously, a large number of 404s to a specific web server. So we can have a look at that one quickly. If it's successfully imported. I mean, who knows now if these things actually import. Correlation directory enumeration, there we go. So we look at an increase in the number of 404 response codes. So the get method and then 404s over that time window. And that's basically it. That's all it'll do. Here, because it's a Sigma rule, it does also integrate nicely with how we set the MITRE attack. So within the reconnaissance, active scanning, and then scanning IP blocks. But it's close enough that it'll work for us in this instance. We can then look at all of the times this is fired from us scanning the web server. So you can then go through, and then an analyst can go through and investigate it and have a look at it. So that is the blue team perspective of the reconnaissance on low security for the damn vulnerable web application. Thank you for joining me, and I'll see you in the next one.